Yeah? Projectile motion is when you shoot something through the air and it moves both horizontally and vertically. Okay, so objects are moving through the air in two dimensions or two directions, right? If dimensions throws you off, directions means horizontally and vertically. Okay, dimensions means the same thing. It's moving both horizontally and vertically. So with your arm, just make kind of the path that a projectile motion usually makes. You don't have to try to make it with your arm, right? Like up and back down, right? For the most part, our projectiles go up and then back down. And we deal with two different types of projectiles. First of which is called a rolling projectile. I don't know if that's the real word. I kind of made that up. Rolling projectile are things that leave a surface, right? They roll off of the desk. Or we shoot it off of a cliff and it just goes straight and then it starts to fall, right? It falls off of the desk. It's going to move horizontally and vertically toward the ground. So rolling projectiles is the first we'll go over. Launched projectiles is the second. That's where something leaves the ground, right? So a ball that you kick from the ground is going to leave the ground at an angle, go through the air both vertically and horizontally, and land, okay, somewhere far away from you. Okay. So two dimensions, throwing a ball, long jump, kicked footballs. All of these are examples of projectile motion. Okay. Anything that moves freely through the air in both horizontal and vertical dimensions is considered a projectile motion. Okay. The thing about projectile motion is that we don't care how the object was set into motion. We don't care about the kick. We don't care about the throw. We don't care about anything before that object becomes a free-falling object. Right? So the second it becomes released from your arm, right, and it starts to move freely through the air, that's where we're focused on. We don't care about the kick. We don't care about the throw. We don't care about what was happening on the table before it leaves the table. Okay? That's important. Okay. When we're looking at projectile motion, we look at things in the horizontal and the vertical direction, and we know that our vertical acceleration is always, no matter what, negative 9.8. Vertical acceleration is always negative 9.8. So you might want to even put this vertical in there. Okay, vertical acceleration is always negative 9.8. What's horizontal acceleration?
How fast the object is speeding up?
Yeah, how fast it's speeding up or slowing down. But there's something we're going to look at here with horizontal acceleration with projectile motion. Okay, vertical acceleration is always negative 9.8. Galileo was the first one to accurately describe projectile motion. What did Galileo also do? Remember we watched the really historically accurate video on Galileo?
Drop the thing from landing tower.
Right. He said two objects that fall at the same, or of the same shape should hit the ground at the same time because mass has nothing to do with the acceleration or the speed of an object. He also predicted projectile motion by understanding that you have to analyze the vertical and the horizontal separately. Okay, so that's important when we talk about our equations. You have to analyze vertical and horizontal. Since we have to analyze them completely separately, that means we're going to have a set of equations for the horizontal components, a set of equations for the vertical components. Okay, which is why last class we worked on, not last class, but the one before, we worked on splitting those angles into horizontal and vertical components. Okay, because all of that's going to go into these projectile equations. Okay, so vertical and horizontal have to be separate from here on out, always. So these are some things that we need to remember, okay, for the sake of our sanity with projectile motion problems. We always assume that air resistance is negligent, right? In high school physics, we live in a perfect physics world, which means air resistance is negligible. Right? We're not taking into account that it might be windy that day. Okay, or that it might slow down as it goes through the air. Okay, we're thinking perfect physics world, no exceptions. Okay, we've made this assumption before that our time starting is always at 0, right? We don't have an initial time and a final time. We just have the time it took for that object to do that motion, right? We don't have initial time and final time. So we always think our initial time is 0 and our motion always begins at time equals 0. Okay, so for projectile motions, it's really important that we think about setting the origin and setting the time at 0. Okay, wherever our motion is starting from, right? That's our starting point. We don't care about anything that happened before. We just care about it as it starts to fly through the air. We assume the motion begins at their origin. So x initial and y initial are both 0. Okay, so really in your variables it should say this, x sub 0 and y sub 0. Okay, because those are our displacements, right? Our initial displacements are both going to be 0. Okay, that's the way that I teach it. Some of you have the ability to flip that around in your mind, right? If I start on top of the cliff, you like to think that, if the cliff's 100 meters, that's our initial displacement. I don't work that way, right? I flip them, but that's fine. You just need to pick a method that works for you. I will always, always, always put the origin at the start of the motion, which means our initial displacements will always be 0. Okay, does that make sense? Okay, that's how I work. If you can flip it yourself, that's great. Okay? If you don't even know what I'm talking about, then just follow me. Okay, then don't try to do anything different. Just follow what I'm doing. Okay. Okay, we're going to look at a ball that rolls off the table first. Okay, so if I have a table right here, and I don't actually have a ball to roll off the table to show you. So I have a table here. The ball is going to roll off the table, right? It's going to leave the edge of the table, and then it's become a free-falling object. Okay, so it's originally moving in this direction toward the edge of the table. So if I'm looking at this type of motion, here's my origin, right? It's the edge of the table. As soon as it becomes a freely falling object, that's when we're starting what we're looking at, right? So the origin sets at the edge of the table, okay? We're going to look at our horizontal and our vertical components separately. So here's our vertical components, okay, of this ball that's rolling off the table. Okay, we're going to just kind of look at this example here for 1 second. Since the instant it leaves the table, it's traveling purely horizontal still. We have velocity in the y direction, initial is equal to 0. Okay, these are the variables that your book chooses to use. Okay, so Vy0 is initial vertical velocity. So all of our variables now will have subscripts that go with them, an x or a y, to tell us vertical or horizontal. So all of those subscripts mean something. You just got to get down the pattern as to what they mean. Okay? Our acceleration in the y direction is negative 9.8, right? Our vertical acceleration is negative 9.8. We should know that. Okay, it's always going to be the case. Our horizontal components now, okay, we're just kind of analyzing all these components separately, and then we'll start looking at it. We have no acceleration in the horizontal direction. No acceleration in the horizontal direction. Why do you think that's the case? As things fly through the air, do they randomly speed up or slow down in the horizontal direction?
No.
They slow down.
They always keep going, but technically they're going downward, right? We're assuming no air resistance, no friction, right? And we're only looking at the point when it's in the air. Things don't randomly speed up or slow down in the air if we exclude air resistance, right? So, horizontally, we have no acceleration for projectile motion, ever. No acceleration in the horizontal direction. Things don't randomly speed up or slow down in the horizontal direction. Okay, so acceleration in the horizontal direction is always 0. No matter what the problem is for projectile motion, there will always be no horizontal acceleration. And we're going to be able to adapt our equations to just take that out. Right? Since acceleration in the horizontal direction is always 0, we're going to adapt our equations to just take it out, so we don't even have to worry about it. Okay? So since we mean there's no change in in initial velocity and final velocity in the horizontal direction, that means that v sub x, okay, or v sub xo are the same thing. Right? Initial horizontal velocity and final horizontal velocity are the same thing because there's no speeding up or slowing down. Okay, so our horizontal velocity doesn't change throughout that whole motion. Okay, so that's where it gets a little tricky. So think about, just picture, a football flying through the air. As it reaches its highest point, what do we always say that it does?
Slows down.
It slows down, and more specifically, it comes to a stop. But does it come to a stop, right? If it's flying through the air, it doesn't stop moving horizontally. It doesn't slow down horizontally, but vertically it stops moving, right? So vertically it comes to a stop, but horizontally it doesn't. Yeah, that's a little tricky. Okay, so just something to think about. We'll get there. Okay, don't get freaked out. It's okay.
So even if the object is accelerating as it leaves the table, it won't accelerate as it keeps going?
As soon as it leaves the table, all we care about is that velocity that it's at when the second it leaves the table. That's right. So once it becomes a freely falling object, it will no longer speed up or slow down. It'll go that exact velocity. Yeah, good question. Okay. So just think about this one. Which will hit the ground first? The ball rolled off the table or a ball released that's dropped straight down from the same height? You don't have to write it down. Just think about it. Which will hit the ground first? The one that rolls off the table, or if I just drop the ball from the same height? How many of you think the one that is rolled will hit first? How many of you think the dropped ball will hit first? Yeah, it's the same. Good. It's the same. Good. It's the same. Okay. Why would it be the same? That's right. Vertical height is the same. Since we analyze vertical and horizontal completely separately, it doesn't matter that that object was moving horizontally at all. All that matters is the fact that they're dropped from the same height. Okay? So here's what it looks like frame by frame. Right? We've got something that's projected. The yellow one is being projected. The pink one is just dropped. So frame by frame, they are falling at the exact same rate. The yellow ball happens to be moving horizontally. Okay? But it doesn't affect how fast it falls. Okay? Questions so far? Okay. So on page 60, you've got two tables. 3.1 is the normal kinematics equations. You should already have those. Table 3.2 is what I want you to put down. Those are your new projectile equations. Okay, and I'll even show you kind of how I want you to write these down. Okay, so how did those get so shortened? Because you only have two of them, and they're extremely short, right? So here's how it works. What do we know about the horizontal acceleration of an object? It's always 0. So if A is 0, anything times 0 is 0. Okay, which means that Vx is equal to Vxo. Right? That's where your first equation comes from. Okay, there's no change in acceleration, which means final velocity equals initial velocity. Same thing again here. If acceleration is 0, that takes out this whole term. So the horizontal displacement is equal to initial displacement, which is usually 0, right? So they left that whole term out, right? Initial displacement is 0, so that means Vxo times time. Right? That's how these equations have gotten so condensed. We're assuming that the initial displacement is always 0, and we know the horizontal acceleration is always 0. Same thing is true for here. If we know acceleration is 0, that takes out this whole term. And if you just have Vx squared equals Vxo squared, there's no reason to have that equation because it looks exactly like this one. Okay, so that's why we only have 2, and that's why they're so condensed. Okay, they left in the x sub o. I don't really care. You can do it either way. Okay, we know that x sub o is most of the time 0, but you're more than welcome to leave that in there. Okay. Vertical equations are pretty straightforward. Okay, I want you to keep in A for acceleration and keep it as the plus. I don't want you to have to think about too many different types of equations. We just know that A is always equal to negative 9.8. Okay, your book put in the negative or the minus, but we don't need to go ahead and do that. Okay, so any questions on those equations? You need to make sure that you have noted that those are projectile equations. These are only for projectiles, and there's horizontal and vertical. Okay, a stunt driver speeds horizontally off a cliff that's 50 meters tall. How fast must he leave the cliff if it's to land 90 meters from the base? Okay, so go ahead and get written down what you need to, and I'm going to draw the diagram for this. Projectiles, it's really important you draw the diagram so you know where your origin is, you know what the motion should look like, things like that. Okay. So by having our origin at the top of the cliff, what does that mean about our initial positions, both of them? 0. So x sub 0 is 0, y sub 0 is 0. Okay, if you don't want to write those down because you just know it, that's fine. Okay, if you're on board with putting the origin there, then that's fine. Okay, we want to say that the cliff itself is 50 meters tall, and he needs to land 90 meters from the base. So that means this distance needs to be 90 meters. What do those tell us in terms of our variables? Displacement final. So our x displacement, how far away horizontally are we going to end up from where we started? 90 meters. Okay, and then our vertical displacement, yeah, good, it's negative 50. So why negative 50? Good, we're ending up below where we started. Okay, so negative 50 there. Okay, this is what I call a rolling projectile, right? He's leaving the cliff, just like when we rolled the ball off the table, right? He's not being launched into the air. He's leaving the cliff and then he starts to fall. So this is what I consider a rolling projectile. So what do we know about our initial velocities for rolling projectiles? What is 0? Which type of initial velocity is 0? Our vertical velocity is 0. Initial vertical velocity is 0. Because when he leaves the cliff, he's initially traveling some horizontal speed, right? That's pushing him forward. And it just so happens that's what we're trying to solve for. How fast must the motorcycle leave the cliff? Okay, we wouldn't be able to solve for this if it was launched, right? Because that would be at an angle. It would be a little too crazy. So we have to know that Vyo is 0. We're solving for Vxo. Okay, or realistically just Vx, right? If the horizontal velocity doesn't change through the whole thing, we're solving for a horizontal velocity. Okay, so what else do we need to know here? Okay, what do we know about our acceleration? Vertical acceleration is negative 9.8. Horizontal acceleration we don't even need because it's 0. Right? No need to write it down. So, let's take a look at our projectile equations now. If our goal is to solve for v sub x or v sub xo, right, we have to find time first. So what's the only connector between our horizontal and our vertical equations? Time, right? Time is the only one that overlaps between those two. So time is going to be our connector between our vertical equations and our horizontal. Okay? Time is going to be our connector between our horizontal and our vertical equation. And more often than not, you're going to use your second vertical equation to solve for time. Okay? More often than not, that's what we're going to use. Okay? So we need to solve for time. We're going to have to use our second vertical equation because we don't know our final vertical velocity. We don't know how fast he was going when he came close to the ground. So we have to use our second one, right? So that equation looks like this. Y equals y initial plus vyot plus 1/2 at squared. Okay? The good news about rolling projectiles is 2 of these terms get dropped because they're 0. Okay, y initial is 0, and our velocity initial in the vertical direction is 0. So for rolling projectiles, this becomes a really easy equation. And our final y displacement is negative 50. Okay, so we should multiply these two together, divide them to the other side, then we square root our answer, and we get a time equal to? Good, 3.19 or 3.2 seconds. Okay, from there, where should we go now to end up solving for our horizontal velocity? What equation can we use now to solve for our horizontal velocity? The second horizontal, right? X final equals Vxo times time. Okay, we know our final horizontal displacement is 90. right? Because we know we're ending up 90 meters from where we started. VXO is what we're solving for, and time is 3.2 seconds. Danny, what'd you have? Good. 28.13 meters. Yes, it should be meters per second. My fault. Right, that was a rolling projectile. This is launch. You can tell the difference because launch projectiles always have an angle that go with them. Okay, so go ahead and get written down what you need to, and we'll start working. Okay, so can we picture what's happening in our motion here? Right, a football's on the ground. We're kicking it from the ground at an angle of 37 degrees with an initial velocity of 20 meters per second, which is pretty fast. Okay, so we're going to have a little bit of a crazy answer here, but that's okay. Okay, we might have an NFL kicker going on right now. Okay, so we want to find two different parts, the maximum height and the time of travel before the ball hits the ground. Okay, so this is what our path looks like. This is a super zoomed in version of that initial kick, right? When it becomes a freely falling object, this is a very zoomed in version. So it's really not going to travel at that angle for very long, right? This is just a zoomed in version so that we can see that initial velocity. Okay, because if our initial velocity is at an angle, we have to break it into its horizontal and its vertical components. Right, because we don't deal with things with angles. So, if I was going to label these components, here's our initial velocity. Can I just put initial velocity in our equations anywhere? I have to have initial velocity y or initial velocity x. Okay, so how could I go about solving for those? Right, which would this side be? Okay, so we would label this v, y, o. Okay, and this would be Vx. Oh, right, those are our initial velocity components. Right, so last class when we worked on breaking down vectors into x and y, right, now we're rolling that in here to find our projectiles. Okay, so let's solve for Vyo and Vxo. Okay, we always have the angle from the ground. Unless we specifically state otherwise, the angles will always be like this north of east, like the most common angle, right? We're going to assume it's going in the positive direction unless it's stated otherwise, okay? So Vyo is the opposite of that, and we have the hypotenuse, so we'll use sine. So that makes it 20 times sine of 37. Make sure your calculator's in degrees, not radians, which is 12 meters per second. Sorry, I'll write out how I found that. I took 20 times sine of 37, and I got 12. Okay, to find the x component side, that's my adjacent side, so I'll take 20 times cosine of 37, and I get 16. Okay, are we on the same page so far? Okay, so whenever we see angles, first thing we do is break that into its x and its y components. Okay, that's the very first thing we do when we see angles.
So when we're given the velocity 20 meters per second, we would never put that into an equation?
Bingo. Once we break down 20 meters per second, it never goes in an equation, ever. Once we break that down, 20 is done, right? We're done with it. It doesn't go in. 37 doesn't go in anywhere. Once we break it down, we're not using 20 anymore. I was just about to say it, so I'm glad you said it first. Okay? Don't plug it in. You will still do it. But don't. Okay? I promise you, some of you will still do it. Just leave it out. Okay. So let's talk. We want to find, boys, chill. We want to find the maximum height. What variable does that mean that we are solving for? Y final. Why not X final?
Because that's out.
That's horizontal, right? We want to find the maximum height. So we need to find Y final. Okay? What is our initial Y displacement? 0. Okay? Do we have the time that it takes to reach peak height? No, we don't. So we're going to have to maybe solve for that too, right?
Is the time it takes to reach peak height going to be the same as it is to get back down to the ground? Okay, so we just multiply by 2.
Good. Okay, so Amanda's pointing out, when we did those purely vertical kinematics problems, if our path was symmetric, that means it takes the same amount of time to go up as it does to come down. Okay? So right now, if we're looking at peak height, are we trying to look at the whole path? We're just trying to look at the first half. Okay? So that means the time we're looking at is just going to be the time it takes to reach peak height. What do we know about an object's vertical velocity at peak height? 0. So that means VYF is equal to 0. Okay, and this is at peak height. Okay, so we really got to take a step back and think about, okay, I'm trying to find max height or peak height. That's only half my motion. So I just need to take that snapshot and look at what variables are happening during that first half of the motion. Okay? So now what equation could I use to solve for time to get to that point? Yeah, I could use the first one to solve for time, and then I can solve for distance final. Okay? What also could I do, Jake?
You can use the third equation to get the y.
Yeah, I could just use a third equation. I don't have to solve for time at all. Okay? So there's multiple ways we can get there. Okay? The reason that I'm going to go ahead and solve for time is because I'm going to eventually need the time of the whole thing. So that's just kind of, an extra step. Okay? It doesn't really make a difference which path you choose, right? Okay, so if I'm going to solve for the time it takes to reach peak height, I know my final vertical velocity is 0. My initial vertical velocity is 12. My acceleration in the y direction is negative 9.8. And this is my time. Okay, this time right here is only to peak height. Okay, and I know that because my final vertical velocity is not going to be 0 at the end of my path. It's only going to be 0 when it's at its highest point. Okay, so you need to make sure we're careful there. Okay, so this is at peak height. I'm going to use that time now to solve for maximum height or peak height. So what equation could I use there? Probably the second, right, since we have time. Okay, Did you happen to use the third equation to solve for displacement, or no? Okay. You could have, right? We could have used the third equation to solve for displacement and then solve for time, right? There's multiple paths you can take to get to your final answer. That's fine. Okay, but did we at least agree that we had 7.35? Okay, and our total time is peak height times 2, right? The time it takes to reach peak height times 2, because it's a symmetric path. It takes the same amount of time to go up as it does to come back down. Okay, so total time is just multiplying that by 2. That little shortcut, right, to find time only works when we have a symmetric path. Okay. What questions do you have? Most projectile problems take more than one equation. I'm just warning you. Okay? Yeah.
When is it not symmetric?
The next problem.
Oh. Will it be stated that it's not symmetric?
Yeah.
Okay.
Yeah. I mean, it'll say, like, we start at a height of this many meters, right? And so then you know it's going to land on the ground. That's what the next one will be.
Oh.
Okay. So, like, if you start on top of a cliff and launch it, right, then it's going to not take it the same amount of time.
Horizontally, isn't it pretty much always symmetric though? At great speed.
No.
Okay.
Horizontally, no. Because it's going to take more time to fall from peak height to its bottom point, so it's going to travel further because it's in the air longer.
Yes, that makes sense. Okay.
Okay, let's try this next one. Suppose the same football was punted from a distance of 1 meter off the ground. How far did it travel before hitting the ground? So now we're not kicking it from the ground this time, we're kicking it from a height of 1 meter. So it's a little bit different. 1 meter is 3 feet. Yeah. I mean, okay, do you want me to make it 0.85 meters? Like, good grief. Just trying to make it easy numbers here, Stone. Lay off. I'm just kidding. Okay. So here, we've got a height of 1 meter, but our initial velocity, our angle was still the same. So there's components here that we can use from our last problem. Right, we knew this is 20 and 37. So our VYO and our VXO aren't changing, right? But here's why it's not symmetric. Here's its peak height, right? It's not in the middle. It's going to fall below where it started, right? If this is the height from which it was kicked, it's going to end up falling below that. So that means the second half of the motion takes longer than the first, right? It's going to fall that extra 1 meter. So what do we know about our final vertical displacement for our whole path? Yeah, negative 1 meter, right? It's going to end up 1 meter below where it started. That's for the whole path, right? We're not concerned about peak height here. Because it's going to end up 1 meter below where it started. If that's the level he kicked it from, it's going to end up down here, 1 meter below where it started. We want to know how far did it travel before hitting the ground, which means we're solving for x. Okay, and I really shouldn't have put this final there, sorry. So, in order to find our final horizontal displacement, what do we need to know? Time. Can we use the same time that we solved in the last problem? No. So, we get to solve the quadratic. Right? We almost always use the second equation to solve for time. Second vertical equation, I'm sorry. Y final equals what? Gosh, your guys doesn't have the final, sorry. Y initial plus VYOT plus 1/2 AT squared. Right? That's almost always the equation we're going to use to solve for time. Okay? Unless you want to solve for final vertical velocity, and then solve for time, and then solve for horizontal. I don't like doing that. It's the same number of equations either way, but. So negative 1 equals 0 plus VYO, which is 12, times time, plus 1/2 negative 9.8 times t squared. So when we start setting this up for our quadratic, we need an A, B, and a C term. The A term, I'm going to rearrange this so it's set equal to 0, because when we have the quadratic, that's what we should always have, is set it equal to 0. So 0 equals negative 4.9 t squared plus 12t plus 1. Okay, do we agree that those are our A, B, and C terms? Okay, go ahead and solve that quadratic for time. We found our time. That wasn't our overall goal for the equation. It's supposed to be how far did we go. So we took VXO, horizontal velocity, times our time to get our final displacement.
Do we have any more?